Hey guys, I'm Christopher McGinnis, and today we are going to be learning how to use Ansys to do some fluid flow analysis. Um, so right now I'm in the Ansys workbench, which is where we'd be doing uh, the setup for all of our work. This is going to include design modeler and some other functions of Ansys. So first we're going to take our fluid flow with the Fluent uh, brackets from the analysis systems and drag it into our project schematic. Um, we have some steps to take to get our experiment ready. Um, our experiment today is going to be working with uh, Pousielle flow, Couette flow, and a combination of the two. Um, Pousielle flow is a uh, flow due to a pressure gradient. So we're going to be taking a velocity at the inlet and showing that as it moves through a rectangular cross section. Couette flow is is going to be the same rectangular cross section, but instead of a velocity inlet, we are going to have a pressure inlet of 0 and a pressure outlet of 0, because we don't want to show a pressure gradient, but we will have the top plate moving at a specific velocity and have no velocity of the initial fluid. And the combination will be a top flow, or sorry, a top plate moving as well as an initial velocity inlet. So first things first, we need to get our geometry set up. There's two settings, or two spaces to use, space claim or design modeler. I find design modeler just to be a little bit nicer. It looks a little bit similar to things like SolidWorks or AutoCAD. So if you're familiar with those, this might seem similar. Space claim also works. It is just not my preference. So totally up to you. All right, so we just gotta wait for design modeler to open up. Let's try that again. All right, so now that design modeler is opened up, we are in our modeling space. One thing to note is depending on what your experiment's going to be, whether that's going to be in millimeters, centimeters, meters, um, I like to start off by going up to the units tab and selecting what units I'm going to be modeling in. This way, for the rest of the equation, the rest of the setup, it makes it a little bit easier. So I'm going to be using millimeter just to make it easier for modeling. We'll also be taking a look at the Z or the XY plane. So from here, you can either use the tree outline XY plane selection, um, or you can click on the Z section or the Z arrow to bring it to the XY plane. So we're going to just use a rectangle to simulate a tube. If you can create a rectangle in Design Modeler, you can also create a cylinder. It's not that much more difficult, but just for simplicity's sake, we're going to use a rectangle. Your initial settings for the program should have everything snapped to either an axis or the origin. So we're going to go from the origin. We're not making any crazy shapes, so this will be the easiest to reference. So we'll just draw out a rectangle. We don't care too much right now about what this is. It's kind of difficult to set up the dimensions from the rectangle unless you're using 3-point. But it also is pretty fast to do it this way, just drawing a regular rectangle and then clicking on the dimensions tab and using the general dimensions section. So just click on an edge. We're going to use the top edge, and this will be the length of the rectangle. And then once again, we'll do it for the side. This will be the inlet. So now we can see our height. Well, technically our length is 23 millimeters, and our height is 5.6. Our height's also going to be our diameter. So if you were looking at this like a tube or a cylinder, this V would represent the the base plate or the inlet of that tube or cylinder, and then this would be the outlet, the right hand side of it, from our perspective currently. So right now we're going to go ahead and our diameter is going to be 10 millimeters for some math that'll be coming up later. And then our length is also going to be 500 due to a 50-to-1 ratio for our diameter to length of tube. Now I like just zooming out and kind of getting an idea of what this looks like so we can see the whole shape. From here, we are going to go back to modeling. And now we have a sketch on our XY plane. We want to take that sketch and turn it into a surface so that way we can initiate and start naming some edges and stuff. So we've created our sketch and we want to just surface sketch. I like to just name mine my dimensions so that way I can easily reference this when I plug it into other analysis. So we're gonna go ahead. That's good. Oop. Just kidding. Okay, that's fine. Let's just keep surface sketch for 1 for now. And then we are going to... So next we are going to generate our shape, or our surface. If you see me scrolling around on the page, if you have a mouse with a scroll wheel, you can hold Control and click the scroll wheel in, and then you can drag or pan the shape around. And if you scroll in and out with the wheel, it's either scrolling in, scroll out to zoom out. Alright, so now we have a part and a body. So we have one whole section. What we need to do is define some edges. So that way we have some geometry to work with when we're doing our calculation setup. So we're going to go ahead and take the left edge and we are going to... Okay, so now we need to move from our current part to the next step of our Fluent flow analysis, which is meshing. So meshing is just going to give us a surface that the flow can flow through. So the program itself can take some measurements. The goal of meshing is to have a high quality mesh so that way we get appropriate results. You'll see a little bit more as we get into this. So once it loads our shape, we can change our settings here. Alright, so we're going to go back to the XYZ plane, or XY plane, by clicking on Z. And we have our mesh. So these look all right. We are going to click on our mesh and we're just going to hit generate. And we have our mesh generated. So we want to go to our mesh and right click it. And we're going to insert a method of mesh. Alright, so we're going to try that again. We're going to go back into mesh and then insert and method. So our geometry is going to be this, our shape that we created, and we're just going to hit apply. Okay. So now that we have our mesh, we're going to go ahead and generate. So we see our mesh generated. But unfortunately, this isn't going to give us any good data, so we're not going to use this mesh. We need to get a little bit more in depth. So we're going to use sizing to pick out edges. We need to actually use the edge selection here, so that way we can pick the inlet and outlet edges. and then hit apply. And then we also want to take our top and bottom walls, this one and this one, and hit apply. So we need to change our element size for both change our type from element size on both the edge sizing for the inlet and outlet and the edge sizing for the top wall and bottom wall. So from the edge sizing, we're going to go to type, element size, and we want to do number of divisions. This way it gives us a little bit more control over the size of our divisions. So we'll use, let's say, 150 for the divisions for this section. And then for our edge sizing for the top and bottom walls, we will use number of divisions. And let's go with 250. And then we're going to go ahead and generate the mesh again. And hopefully that will give us a better view of our mesh. Alright, so if you notice, our mesh looks a little goofy, especially towards the inlet and outlet edges. That's because we also need to make sure that we change the behavior of the mesh from soft to hard, since we are using a fairly, very hard edge shape. So once we've changed that, we'll go ahead and generate again and hopefully show that our mesh looks a little bit neater. So a little bit goofy from the lines, just kind of looking at it, but alright, so this is actually a good learning point. Messed up a little bit with the meshing, so we're gonna try this again. Unfortunately, when I created the sides, I didn't do them in an appropriate order, and my edges were all clumped together. So we're gonna go ahead, do this again, insert, sizing, and we want edge selection. We're gonna do the inlet and outlet edges. Okay, and then we're gonna hit apply, and we will hit generate so you can see what this looks like. So then we are going to go in and from element size change to number of divisions, and we want, let's say, 150 divisions, and we want our behavior to be hard since we have a hard shape. There's no round edges, there's no filleted edges, so this will just make it a little bit fill in this shape a little bit better. So we'll hit generate. Okay, so now we have a mesh, and it looks a little goofy, but that's because we're only meshing on the inlet and outlet and not meshing from the top and bottom walls. So we're going to do sizing again. We're select the top and bottom, and we're going to hit apply. Then we're going to change from element size again down to number of divisions. Let's use 400 instead of 250. And we also want to use a soft mesh, or sorry, a hard mesh instead of a soft mesh. And we will generate that again. So hopefully now our mesh should look more uniform. There we go. Alright, sorry about that, guys. Alright, so we also need one final mesh, which will be the face mesh, to help us kind of clear up these edges where they, they start to get a little bit non-uniform. So select our geometry, and we're going to go ahead and hit apply, and this should clear up some of these edges. So we'll generate that mesh. And there we go. So now our mesh should look, we're going to go ahead and zoom in, should look fairly uniform. So that's how it should look. That way it's just a high quality mesh. It should give us some pretty consistent results. Okay, we'll go ahead and zoom out to fit this. The next thing we want to do is add some named edges, so that way when we get into the solution setup, we are able, or the calculation setup, we are able to designate where the flow is coming and where our boundary layers are. So we went ahead and select the edge tool. We're going to click on, or right click on the left edge, which will be our inlet edge. Let's select it, right click, and we want to create a named selection. So I'm going to call this the inlet, and we'll keep this the same. Okay, and then the next one we're going to do is our outlet, which is the right hand side of this. Same thing, name this the outlet. And then we also want to select the top. And you can name this, you know, however you want to, say top boundary or top wall. And that should be it. So now that we have our name selections, we are going to go ahead, we can exit out of this, and we're going to go back to our workbench. So now we need to update our mesh. It'll just pull that mesh that we created. And then once we finish up with the mesh, we're going to go into the fluid flow setup. All right, so now we will update this as well. And we'll double click and enter setup, just to make sure that it's pulling the mesh we just created. All right, so we'll double click into setup. We want to use double precision, just so that it's storing a 64-bit. It's 64-bit instead of 32-bit. Most computers nowadays are 64-bit operating systems, which means it can just hold decimal, or the largest number it can be is, you know, 10 to the 308 or something. Same thing with small numbers, so it's 10 to the negative 308. It just gives us a more accurate calculation. We don't need to worry about processes or GPUs. If you have a GPU, you can use that. Or if you have a GPU in your computer, which if you're running this, you might, unless you have integrated graphics. But we're not working with anything that complicated, so we don't really need to. We'll go ahead and click start. All right. So it's going to bring up our model that we created. And this is where some of our math's going to come in. Okay. So we've got our model here. And we have some general selections to make. We're going to be using pressure-based. Other types of solving we can do are density-based. We're not worried about that right now because ours is, some of our calculations are going to be due to pressure gradient, and that's what we want. We do want steady as well as planar or planar. We're not doing any asymmetric items with our rectangle, and we're using absolute because we are just showing a concept. We're not showing an actual real life model. We want to go to viscous, so we want to open up models and we want to go to viscous because we're going to be using a laminar flow instead, just to make everything a little bit easier, and conceptually that's what we care about. I'll close that. Now we want to go into model or materials, and we're going to be using a fluid. We're going to be using air. So one of the things where the math kind of comes in with this is we need to change this to make sure our Reynolds number is below 2000. So we're going to keep our density at 1 to make the math a little bit easier, as well as the viscosity. We're going to change that to 0.001. And I can show why this is important. Okay, so how I was talking about, our Reynolds number needs to be laminar. In this case, in our tube or a rectangular cross section, our Reynolds number to have a laminar flow needs to be less than 2000. To make sure we're not hitting any boundaries and getting weird outlier information, we're going to set our Reynolds number equal to 1000. And to do that, we have an equation. Reynolds number equals the uh, density, which is rho rho of infinity. Sorry, because we're taking conceptually, this is what we care about. The velocity. This is the not the specific velocity, or this is the universal velocity, not the specific velocity. And then the diameter of the pipe cross section. Ours is just the height because because it's a rectangle. And then this is all going to be over the viscosity of the fluid, which is mu infinity. All right, so that means with what we set air to, we could have kept it at 1.225 and done some extra math to figure out what that is, but we can change it to show conceptually what we're talking about. So our density is just 1, and obviously there are units involved. Density is kilograms meter cubed, but our Reynolds number is unitless, so it's good to know the units and understand how those work and cancel each other out. But if you have questions, you can always check the link in the description. I will provide those units for you right down there. So anyway, we have 1 as our density, and we're going to use a 10 meters a second velocity, as well as our 10 millimeter 10 millimeter height. Now, this is standard units, so the normal equation is in meters. So that way our velocity is in meters a second. We set our model up to be millimeters. But we'll have to convert for our formula. And then this is all going to be over our viscosity of the fluid. And actually, sorry, this is 10 millimeters, not 1 millimeter. And then so our viscosity has to be 0.0001, and that, if you calculate it, will give us a Reynolds number of 1000. So that's important to remember, just to make sure that you're staying within a laminar flow. And that's what we're trying to show today. All right, so we're back here. So 0.0001. And then we'll go ahead and change that so that way it stays. All right, so now we don't need to worry about cell conditions. This is just if you need to do some other calculations depending on the material that you're using, but we're not going to be worrying about that. But we do need to change our boundary conditions. So I mentioned that we were going to test 3 different types of flows. I'm going to model only 1, because the other ones are just different selections based off of the boundary conditions. So a Pousielle flow is having a velocity inlet with a pressure outlet, because it's based off of a pressure gradient. And then a Couette flow is a inlet that is a pressure inlet and an outlet that's a pressure outlet. Because we set that because we set the pressure to 0 on the inlet and the pressure outlet to 0 or 0 pascals on both sides, um, to make sure that we don't have a pressure gradient. But in the first case for Pousielle, our top boundary or bottom boundary, it doesn't really matter. The top boundary, you'll get a little bit different velocity profile, but the top boundary or the bottom boundary needs to be moving, or sorry, needs to be stationary, or both need to be stationary with a velocity inlet. Versus the Couette flow, you won't have a velocity for the inlet, but you will have either the top or the bottom boundary moving at a specific velocity. So we're going to use a combination. So we're going to go ahead and keep a velocity inlet because we are going to be using both the Pousielle and the Couette flow. So we'll set this to 10 meters a second, which is important because that formula I showed you earlier, as well as we're going to make our top boundary. Select this, and in here you can, this is where you can see stationary or moving. We are looking at a no slip condition, just to make all the math work a little bit nicer and show a conceptual view of the flows. So we want a moving wall, and 1 in the positive x direction just means like this is true, so you want it to move in the positive x direction. If you put -1, it would be moving in the negative x direction, but we want it moving to the right. So we'll also set our velocity of the top plate to 10 meters a second, and we'll go with that. Okay. So it looks like our boundary conditions are set up appropriately. If you need to change from a velocity inlet, just to kind of show you how to do that, so you right click on the inlet, go to type, and from velocity inlet, you would just go to pressure inlet. So in case you need to change that for your Couette flow, that's how you do that. All right. So that's set up. We don't have any weird reference frames we need to set up. Our mesh is already set, so we don't need to mess around with any of this. Our walls are set. We're only using the top wall in this case, or top boundary wall. But what we do need to do is go to initialization. We're going to use hybrid initialization. It does a lot of the work for you. If you have specific conditions that you want to set, you just go into more settings. If I can show you what that looks like. So number of iterations, we're going to be changing that in our calculation settings. We're not too worried about it here. So we're going to go ahead and hit OK. We're going to hit initialize. And then we're going to go to run calculation and double click. Most of these selections you have to double click to open them up, just for future reference. And then number of iterations. The number of iterations really depends on when the values are going to converge. So the more iterations you have, the longer it will take. But it will make sure that if you have any outlying cases of values, that if it doesn't converge, it'll stop at this number 500. So if your math was really wrong and it just didn't happen to work out well, it might not meet this 500 iteration convergence. This should converge in around 50 iterations. So now that it's that set up, we don't need to mess with any of this. We're going to go ahead and calculate. And it'll start with our iterations. And it took a little bit longer, but not terrible. Still within our parameters. So now we want to take a look at our contour to make sure that we have an appropriate velocity contour. So we're going to hit velocity contour, and then if we just hit save and display, it'll do a good job at automatically selecting what we want to look at. And then the other thing we can do is drag this to the top to give us a little bit more space. And then we're going to click on this box to fit to the window. So we have a better view of the whole rectangular cross section. So let's close this. So right now we're looking at the velocity contour. So you can see the inlet, the velocity of the inlet is high, not 100% the fastest velocity that it can reach. Actually, let me bring this back to the side so we have some numbers. So this is the velocity magnitude. This is actually 13 meters a second, or some decimal value. This is just saying 1.3 times 10 to the first. So it's 13. It could have some extra decimal points in there. We're gonna look at that when we get to our solution section and not in our calculation section or our setup. But this is kind of what that means. So with the initial velocity being 10 meters a second and the top plate moving at 10 meters a second, we should experience a faster flow. But when it starts, it should be close to that 10 meters a second because that's what it's coming in at. And you can see at the end, it starts to reach that maximum velocity. Or, I mean, it starts somewhere around, about a third of the rectangular cross section. But we know that it's a fully developed flow, hopefully at the end. And we can see that 13 meters a second being the max velocity. And you can start to see where that boundary layer starts to happen, and that flow separation starts. And we can actually, where that first little blue section is, we have zero velocity happening. So let's go ahead, zoom out. We don't need to do too much more with this. We're going to go ahead and just close this. We'll go ahead and save this. That's what we're using it. And just let it work through. So now we're going to go to our results section. Solution is the solution that we created inside the calculations. So you no need to worry about that. We're going to go ahead and load up our rectangular cross section. And now we need to create some views so that we can see what we're looking at. The first one we're going to go to is we're going to create a contour of our shape. And let's just call this combination contour, so that way, a little bit neater. All right, sorry about that. So we want to look at the velocity of view. So kind of recall our plane is XY. So the U direction will be X, V will be Y, W and the Z. We're only two-dimensional, so we don't care about W. And we are trying to find the velocity in the X direction. So we're gonna go velocity U, and the range is going to be the range is going to be global. You can select your own local values, or specify values. But we only have one model, so we're not too worried about that. And then we'll go ahead and collect. We're gonna go ahead and actually change the contours, just to make it a little bit more. Once again, we're just going for the sake of clarity. The more contours you have, it gets a little bit more detailed. If you have too little, you'll miss out some of the smaller details. If you have too little, you miss out on the smaller details. If you have too many, our model's not very large, and we'll lose some. There's a marginal return on that. Go ahead and click apply. And actually, another learning moment. Sorry, guys. We forgot to change the location of our combination velocity contour. So we want to use symmetry 1, just so that way it's taking the symmetry of our rectangle and not of the bottom boundary or the top boundary. Let's go ahead and apply that again, and it should, there we go, should show that velocity contour we looked at earlier. So now we have that. We're gonna go ahead and also show so that's how you show your velocity contours. We're also going to go ahead and go over to chart because we'd like to see the velocity profile. So to do that, we go over to chart and let's just do combination profile. We could also make sure we put velocity in here. That way it keeps it organized. Okay. And we'll have to set up our details for the combination velocity profile. Once again, we're doing XY. We'll name our graph. Let's do velocity combination, or sorry, combination velocity profile. And then we're going to go ahead to data series and mess up again. So sorry, I did mess up. We're going to hit, I can't cancel it. We're going to just cancel this. So we actually need to go in and insert some lines to make sure that our chart pulls some data points. So that way we can see what our, or the Ansys program can actually take those measurements. So we'll do it at, let's say our total distance is 500 millimeters. We can do that at every 125 millimeters. So we'll name line 1 as, let's put quarter line, and then our point 1 is going to be for the x direction at 0. Oh, you know what? That's not going to be the quarter line. That's fine. We'll use this. Quarter line is going to be 0.125 with a initial y height of 0, and then also the same x location, but we want a height of 0.01 or 10 millimeters to match our model here. And we'll make it 100 samples at that line, so that way it takes a decent amount of these. And actually, I'm going to turn off the contour so you can see that line. We're going to go ahead and insert some more lines. We'll insert one at, let's go, beginning. And you can do this however many times you want. We just want a good good selection of lines to kind of see it in our chart on how our flow develops. So we'll make a couple more of these, do half. And this will be 0.25. These are all in millimeters, or sorry, these are all in meters, and so we need to make sure we're converting from our millimeters because there's no unit selection here. 0 for the y, and then 0.25 and 0.01 for halfway point. And that way we're just making sure it's looking at the whole section. Go ahead and add another line. Let's call this 3/4. And this will also be 0.375, 0.375, and then 0.01. Make sure we do 100 samples. Apply that. If you ever mess up on these, you can always go back in and change them. And we'll put the end. So not a big deal if you happen to mess up. It's pretty forgiving. Okay. So we'll just verify our lines, make sure they're all taking 100 samples. This one isn't. That's because I'm rushing. I apologize. Okay. So we have all of our lines set up, and you can see them clearly on our model. So this will allow us to set those data points in our chart. So we go back to the chart, and we want to go back to the chart selection up here. And let's name that again combination velocity profile. I'm going to make sure keep it similar. Okay. And so for these guys, the data series, I'm going to name them according to my lines. We want to make sure that we're selecting each of these. We have to create a new one for each one. So let's go ahead and just create that. Beginning, quarter, and each time you have to make sure you're selecting the appropriate location for that line. Okay. And then we're going to go to the x-axis, and we need to make sure our variables match what we're looking at. So initially we set our x-axis to be our velocity u, and then our y-axis is actually going to be our y because it's based off of the height. You want to see our velocity in relation to our height. Okay. If you care to have more clarity or, to a higher degree of accuracy, you can change the axis formatting. Right now it's to 3 decimal points. It'll do it automatically, so I'm pretty sure once we hit apply, it'll look at 3 decimal points. But if you want more, you can always change that. Those look good, so we're gonna go ahead and hit apply, and it's gonna create us some lines to look at. So the beginning is going to be a little weird because we start off exactly at 10 meters a second with regard to our y-axis. And so, 0, so at the very beginning of our y-axis, we said, hey, our velocity is 10 meters a second, and it's a square, which that makes sense. And then as you get further and further out to the end, you start to see our velocity profile start to hit that combination. So with a Pousielle flow, I'm going to see more of a parabola because the top and bottom walls are stationary, and based off a no slip condition laminar flow, the velocity at the top height and the velocity at the bottom height should reflect each other. Obviously, if you have, you're going to, in real world application, you're going to have, artifacts on your tubes that'll, cause instances of turbulence where the flow won't be as laminar. You're going to have some friction, both from boundary and from fluid. But in this case, we're just trying to show the conceptual portion of this. So in this case, in a Couette flow, it's more linear because that top plate, as it travels, the friction from the top plate, or the fluid friction from the top plate, is going to create a almost a linear velocity of that fluid. So we can kind of see how that affects our velocity profile with both the initial velocity here at 10 meters a second, and then the almost parabola shaped fully formed flow here, and it's skewed towards the height to the top of the plate. If the bottom plate was moving at 10 meters a second, you'd see this skewed towards the bottom, and because ours was the top plate, top wall, moving at 10 meters a second, the top plate is skewed, or the velocity is skewed towards the top of the height. So this should make sense. We could go back and change the bottom plate to move, and you'd see this move down. You could, make it stationary, and then see a a Poiseuille flow, and see a perfect parabola or close to perfect parabola, and then a Couette flow. If you remove the velocity inlet and turn that into a pressure gradient, so there's no initial velocity, just the velocity of the plate or the top wall, you'd see that move linearly. So that is pretty much all we have for that. There's more things you can do with this. You can make this pretty, but just showing conceptually what you can do with this to see what those flows would look like. Um, this is pretty much the basics of doing that. So I hope you enjoyed, and we'll see you next time.